This video will discuss the topic of linear systems. Before we begin, let's take a look at the review and reflect. We should be able to graph on a graphing calculator the two equations and find the point of intersection, and then state the point of intersection as an ordered pair. You may want to pause the video here and try this on your own. The steps to use in a calculator after you have submitted the first equation under y1 and the second equation under y2 is to use the second button and then the trace button. It's actually the calculate button. On top of it, it will say trace. And then click number 5. When I taught high school, I would say this was combo number 5. And then you're going to press the enter button 3 times. And what it's doing is that it is asking for the intersection, that's what the 5 says, and then it's asking for the intersection of the first equation, the second equation, and then take a guess. You can guess or not, but either way, it's going, when you push enter, it will give you the result that the point of -3, 5 is the point of intersection. If we want to see it as a solution set, don't forget to put it in curly brackets as a solution set. For the reflect, that just means that after we finish talking about linear systems, you should be able to write down directions to solve a 3-equation system by elimination. So let's get started. So the first thing we want to do is to talk a little bit about notation. We will see that a system will be put into one curly bracket, and most likely they will name them as equation number 1 and equation number 2. Sometimes we can use letters to name our equations. It kind of beats the idea of having to say the entire equation over and over again. We can just say equation 1 and we know it's the top one, or equation 2 and know that it's the bottom one. Remember that our solution set will be in curly brackets and it will be a point. So let's review what we know about 2-equation systems. First thing, we know that we can either have a system that is 2 parallel lines. So I'm going to denote that by drawing them here. So we can have 2 parallel lines, or our 2 lines can be intersecting. So I'm going to draw 2 intersecting lines, and when they intersect at one point. Or the other solution can be that our one line is actually the same line. So we can actually have 2 names for the same equation and we have infinite many solutions. The same thing can be said with 3-equation systems. The only difference is, instead of looking at lines, we're going to be looking at planes. So that could be one plane, this could be another plane, and this can be another plane. And we see that there are no points that they have in common. The most famous 3 planes intersecting at one point would be our 3-dimensional origin. So it's harder to draw 3 dimensions in a 2-dimension space, but here's one of them. And then the other one would be coming towards you from the back, towards you this way. So it's back there, there's our plane. And then the last one would actually be horizontal. So it would actually come across the front and then go towards the back and end up here. And what we find is that all of these planes intersect at one point. That we would be on the plane, the horizontal plane will be on this vertical plane, and will be on this vertical plane as well. And then another way that we can see that they actually share infinite many might be like if you had a standing book. So we would have one going through there, another one coming through here, and then maybe another one coming out of the page. And we can see that this line right here is the line that they have in common, and they would have infinite many solutions. Again, I think there's a video that will show you better pictures, but I just wanted you to get an idea of that. What these represent is a number of solutions. If we have parallel lines or even parallel planes, we will get no solutions. We will actually get zero number of solutions. If we do have a solution to a system, a unique solution, we will have one solution, or we can have infinite many solutions. What does our solution set looks like? We can either use an empty set like this, or we can use the null space, which represents an empty set. This figure down here is what we call the null space, so I'll write that down. That is null space. If you have one solution, if we have a two-equation system, we kind of said that it would be a point, an ordered pair. If we have a three-equation system, it will still be one point, but it's what we call an ordered triplet. It's going to have a value for x, a value for y, and a value for z. If we have infinite many, we should have known that we can either put it as x arbitrary, y arbitrary, and z arbitrary. So I'm going to put that here. What we did is when we had a two-equation system, it was just one of those equations. But now we have three planes, so we have to figure out an equation for this line, and we're going to do it such that z will be our variable. So z arbitrary would actually be the point in which we have a function for x in terms of z, a function of y for y in terms of z, and then z would be arbitrary, some number that we would get for z. So again, like I said, we'll see some examples of that in the videos. We have names for these systems. If you have parallel or no solution, we call that as inconsistent. And we would find, if we're solving this algebraically, that we would get some inconsistent stuff with reality, like 0 is equal to 3, or 5 is equal to 17. We will get something unusual that's not true, that's inconsistent with reality. If it does have a solution, we say that that system is a consistent system. So we will have a consistent system if we have one solution. We will also have a consistent system if we have infinite many solutions. So how do we tell them apart? If you have one solution, we call that independent, consistent, and independent. And if it's consistent with a whole bunch of solutions, we call it dependent. And we can see that when we talked about z arbitrary, that the values of x and the values of y depend on the value of z. And that's why it's a consistent dependent system. When we're solving, our consistent dependent system will say stuff that makes sense, like 0 is equal to 0, or 3 is equal to 3. For a consistent and independent system, when we're solving, we're actually going to find some number for x, some number for y, and some number for z. Remember, that number can be 0, or it doesn't have to be 0, but I do want to let you know that you are actually solving. So in other words, the x, the y, or the z do not disappear like it did algebraically for the other two types of systems. Now, I know we haven't talked about matrices, but we will. And when we find matrices, so we're just going to draw this out right now just to complete this table. But for a three-equation system, we don't use it quite too much for a two-equation system, but we can. We would first get what we call the identity matrix. So we would try to find a whole bunch of ones and zeros. And we would get a number for the first one, a number for the second one. But the last one, we would actually get something like 0, 0. And instead of a 1 here, we would get a 0, and then we would get a 3. And this would represent the exact same thing we have up here. If we had a consistent and independent system, we would have an identity matrix, which looks like this. So let me show you what the identity matrix looks like. again, a whole bunch of ones and zeros, and we would have a number here that says x is equal to this number, y is equal to this number, and z is equal to this number. And in the last case, we would still have a identity matrix looking thing, so we would have something that looks like this. Maybe we have a number for x, we have 0, 1, 0, maybe we have a number for y, and at the bottom we will have a whole row of zeros, and that would represent 0 is equal to 0. And that concludes this video.